Hello, and welcome back to the UPC++ tutorial. My name is Dan Bonacea, and I'm one of the engineers at Lawrence Berkeley National Lab who works to develop the UPC++ and GasNet libraries. Hopefully by now, most of you have had a chance to work Exercise 2 and gained some experience in using distributed objects, so let's go ahead and look at one possible solution. So our task was to use a distributed object for the bootstrapping setup stage of our Jacobi application, where we exchange the global pointers that are used for communication later during the time-stepping loop. In this solution, you can see we've declared two separate instances of dist object, where the value type is a global pointer to double. We've initialized the local representative of each distributed object with the corresponding global pointer to our local grid cells. This function is called collectively, so all the ranks are running the same code and taking analogous actions. So after constructing our two dist objects, we invoke the dist object fetch member function, passing it the rank of the process whose value we wish to fetch from the distributed object. The call to fetch will initiate an asynchronous communication operation to retrieve that value from the remote ranks slice of the dist object. Because it's asynchronous, fetch gives us back a future of global pointer double, and we invoke the wait function on that future to stall for the resulting global pointer, which we then store into the appropriate global variables writeOldGrid and writeNewGrid that live on this process. Now, if we wished to overlap the communication for these fetches, we could have launched both these fetches and then separately waited on the resulting futures, but here we've kept it simple for the purpose of the slide and just performed the fetches synchronously. Although all the ranks run this code collectively, it's important to understand that they are not necessarily running in lockstep. As we mentioned, synchronization in UPC++ is always explicit. We previously also discussed that the dist object fetch method ensures that one rank cannot fetch the value from another rank until that target rank has constructed the dist object, because the asynchronous fetch operation stalls until the dist object is constructed at the remote rank. So that means we don't have to worry about races between dist object construction and incoming fetches from other ranks. However, that protection does not analogously apply to destruction of a dist object. So it turns out that we want a barrier synchronization here to ensure that all the ranks have completed their lookups on the distributed object before we return from this function where the dist objects go out of scope and run their destructors. There are alternate ways to solve this synchronization issue, such as allocating the dist object in heap memory so that it doesn't get destroyed immediately upon function return. However, as we've written it here with the dist object as a stack allocated variable, a barrier synchronization before return is the simplest approach to avoid a premature destruction for the purposes of this utility function. Now we'll look at a second and better solution to the same exercise. In this version, we'll instead declare just one distributed object with a value type of stdpair, a container holding two global pointers to double. This pointer pair type alias was declared here to represent that helper type to make the syntax nicer. For those less familiar with C++ programming, it's worth noting that type aliases like this one are a handy feature that can help declutter your code, especially when lots of template types are involved, as those tend to inflate the syntactic length of your types. Here we're using stdpair, but this is just one option. You could get the same effect using stdtuple or stdarray. But in this version, we've chosen to use stdpair. So we declare a distributed object to contain the value type pointer pair. Each rank initializes their local representative of the dist object with an initializer list comprised of the global pointers of their local grid cells, so that's old grid gpointer and new grid gpointer. Next, each rank invokes the dist object fetch member function, passing in the rank of their right neighbor, and invokes waits on the resulting future. In this case, the wait call will return a pointer pair value, which we then assign into the global pointer variables that live on this process. We've done that assignment using the stdtie shorthand introduced in C++11, which is just a syntactic convenience for storing each element of the pair into the corresponding variable. However, one can alternatively store the pointer pair value into a local variable and retrieve each component individually, as demonstrated in this comment. Now, the reason this solution is preferable to the previous solution is that we've aggregated the communication for the two values we need to retrieve into a single fetch operation. The distObject fetch function is implemented as a very thin wrapper around RPC, so that instead of launching two separate RPCs to our right neighbor, this solution instead sends a single RPC that retrieves both the pieces of information that we need. As before, the barrier at the end ensures that all ranks have completed their fetches before we return from this function and allow the distObject to be destroyed. Now that we've discussed some of the basic programming constructs provided by UPC++, we're going to change topics somewhat and see how to apply UPC++ in the context of a new problem, one that arises frequently in certain classes of irregular scientific applications. A distributed hash table, or DHT, is the distributed analog of a STD unordered map. In case you're unfamiliar with STD unordered map, it's a key value container that is basically just a hash table. So our DHT is an associative container that maps keys of a given type to a value stored somewhere in the system, and the memory containing those key value pairs is distributed across processes. This same concept is also often referred to as a distributed key value store, and it comes up in a variety of scientific computing domains. Later in the tutorial, we'll discuss a major genome assembly application called MetaHitmer that is written in UPC++ and relies on a distributed hash table as one of its most important data structures. Our distributed hash table provides methods for element insertion and lookup, where each such operation potentially entails fine-grained and irregular communication with remote processes. We will see how UPC++ makes it very easy to implement such a distributed data structure, and that the result can provide seamless asynchronous operation and robust scaling performance. For demonstration purposes, we'll be using keys and values of type std string in our DHT, but the same concepts apply to other types. In implementing a DHT, we want to spread the storage of key value pairs across processes so that ideally we achieve a good balance across the system of memory utilization for storing the data and network traffic to access it. The basic implementation approach will be to use a hash function to partition keys into a fixed number of buckets equal to the number of processes. We represent the distributed hash table using a collection of std unordered map containers, one on each process, which stores the set of key value pairs comprising the partition owned by each process. DHT access operations for a given key will be implemented using RPCs that travel to the owning process for that key and perform the requested operation on the map, which represents the local partition of the DHT. Now, since we're good object-oriented programmers who believe in encapsulation and abstraction as an important part of software engineering, we'll package all this up into a C++ class that provides a nice, friendly DHT interface for use in application code. So here is the basic skeleton for our distributed hash table class in UPC++, which we've named DistorMap. On this slide, we're looking at just the private members used by the implementation in subsequent slides. We are going to use a distributed object internally to store the hash table partitions, as the abstraction maps quite nicely to the desired approach of managing one representative map per rank. So you can see that we've defined a helper type here, which is a dist object where the value type is std unordered map from string to string. Here we're using string because that's our key and value type for this DHT. One could easily imagine making this a template class, parametric on key and value types, but for simplicity we're just going to use string in this example. We declare a field of our class called localMap having this dObjMap type. That means this field localMap is a distributed object where each local representative is a std unordered map container that holds the keys and values that comprise the DHT partition owned by that process. The curly braces initialize this field to start with an empty map. The outer set of curly braces are for the dist object, and the inner set are for the empty unordered map. Finally on this slide, we see a helper function called getTargetRank. This function is what we use to compute the bucketing of DHT keys into hash table partitions, abstracting that detail out of the rest of the implementation. It accepts a std string key and computes the rank number that owns the partition of the DHT containing that key. To do this, it invokes std hash to compute an integer valued hash of that key then mods that value against the total number of processes, which is provided by the UPC++ rank n function. Thus, we generate an integer result between 0 and ranks -1, which corresponds to the rank number of the process that owns the given key. We'll use this helper function as part of implementing the DHT access operations. If an application wanted to use this distr map class, it would construct an object of this class collectively across the ranks. That construction would in turn construct the local map field, creating the dist object across the ranks to represent the initially empty partitions of the DHT. The application could then proceed to invoke DHT insert and find operations on the key value store using the public member functions whose implementations we're about to see. So let's look at what it takes to implement insertion of a key value pair into our distributed hash table using the representation we've just seen. So here we are showing a member function of our DHT class called insert. It takes key and value strings as arguments and performs an insertion operation in the DHT, returning an empty future which represents completion of the asynchronous insert. As you can see, the implementation of this operation using RPC and UPC++ is actually very concise, so let's examine how it works. We start by calling the getTargetRank helper function we saw on the previous slide, and pass it the given key in order to compute the rank of the process that owns the DHT partition where that key should reside. We're effectively adopting an owner computes rule here, where the rank that owns the key in question is responsible for performing the actual hash table insertion operation. So this is an example of RPC, where we need a remote process to perform some useful work on our behalf. With that owning rank in hand, we're building up an RPC invocation that will transmit the key value pair we're inserting over to that owning process for insertion into the map. The first argument to our RPC is a reference to the local map field of our DHT object. Recall this field's type is actually a dist object. Here we are relying upon a special interaction between dist objects and RPC. When we pass this reference to a dist object into RPC, the UPC++ runtime notices this is a dist object and implicitly converts this argument into the universal name associated with that distributed object. So this dist object reference argument is implicitly converted into a universal name that is sent over the network to the target process, and upon arrival that name is converted back into a reference to the target's representative of the same dist object. So the result is that by passing a reference to our local dist object field, we are ensuring that the RPC callback running at the target will receive a reference to its corresponding target representative of the same dist object. If by chance this RPC message were to arrive before the target process had constructed its corresponding representative of the dist object, the RPC callback would be automatically deferred until after that construction has occurred. The other arguments to the RPC are the key and value strings. These will be serialized in a straightforward manner and sent across the network. Upon arrival, they will be reconstituted as equivalent strings at the target process and passed into the RPC callback. UPC++ automatically supports serialization for a variety of C++ standard types and containers, including stdstring, and we'll hear more details about object serialization later. When the RPC function call executes, this message is injected into the network, carrying our 3 arguments and a pointer to the callback code. RPC injection is an asynchronous operation, so the initiating process does not wait for the communication to be delivered. Instead, it returns a future, which in this case is an empty future, and that future is returned to the caller of insert to represent asynchronous completion of the insertion operation. After the RPC message arrives at the target process, it will induce that process to run the provided RPC callback. The RPC callback is a Lambda function that takes 3 corresponding arguments. The first, lmap, is a reference to the distributed object, which upon invocation has been converted into a reference to the local representative of the dist object at the target process. Recall that this dist object contains the std unordered map container where we want to insert the key value pair. When we apply the star operator to that dist object, we get a reference to the local std unordered map itself. With that in hand, we can invoke the normal square bracket indexing operator provided by std unordered map to store the provided key and value strings into the map. This RPC callback does not explicitly return any value, but this flavor of RPC still entails a round-trip communication operation. After the RPC callback returns, an acknowledgement message is sent back to the initiating process to indicate the RPC callback has completed execution. After its arrival, that acknowledgement message causes the future to be readied, thus signaling to the caller of insert that the asynchronous insertion of the key value pair into the DHT has completed. Next, let's look at how we can implement a lookup operation on our DHT. Here we're showing the find member function of our DHT class. It accepts a key string, initiates an asynchronous lookup in our key value store, and returns a future of string that will eventually contain the value that was retrieved from the DHT. As with insert, we'll start by calling getTargetRank to compute the rank of the process that owns the DHT partition containing the given key. We will be injecting an RPC message destined for that rank. As before, the first argument to this RPC call is a reference to the local map field from the DHT object, which is our dist object. As before, this argument will be converted into a universal name for transmission across the network. The second argument is the key string we are looking up. These arguments are packaged up along with a pointer to the RPC callback code, and a message is injected across the network to the target process. After the message arrives at the target process, the Lambda function that implements the RPC callback will be invoked at the target. That callback will be given two arguments. The first argument, lmap, is a reference to the local representative of the dist object that contains our local partition of the key value store. The second is the key string that we are looking up in the DHT. We start by checking whether the given key is present in the DHT. Here we use the dist object arrow operator, which follows the usual C++ convention familiar from pointers in that it's equivalent to the combination of a star operator and a dot operator to access object members through a level of indirection. The arrow operator is applied to lmap and used to invoke the count member function of the std unordered map object, which is contained in the target's representative of the dist object. If that count returns 0, it means the requested key is not currently present in the DHT, and our callback returns a special string constant indicating the lookup failed to find a corresponding value. Otherwise, we know the requested value is present in the map. We apply the star operator to the lmap dist object, yielding a reference to the std unordered map, and then apply the map's square bracket indexing operator to our key and return the resulting value string. The callback returns a value string, and this string is packaged up into an acknowledgement message that returns to the process which initiated the RPC. After that acknowledgement message arrives, it fills in the value of the future that was returned by the find function and signals its readiness. This signals to the caller of the asynchronous find operation that the find has completed and yielded the provided value. So the key takeaway here, pun intended, is that the irregular and asynchronous communication which is used to implement a distributed hash table can actually be expressed very concisely and naturally using RPCs in UPC++. So for our next hands-on exercise, we're going to ask you to implement two additional member functions on this same DHT class. The code skeleton for this exercise is located in the ex3.hpp file in your tutorial exercises directory. You can build and run a test on this code skeleton with the command make run-ex3, although of course the test won't pass until you fill in a correct solution to the exercise. The first function we'd like you to implement is an erase method, which accepts a key string and removes the corresponding key value pair from the DHT. It's an asynchronous operation and returns an empty future, which is used to signal completion of the erasure. Once you've implemented that correctly, the test should print erase success to the console, and then it will encounter an expected assertion failure when testing the second part of the exercise. The second function we'd like you to implement is an update method, which takes a key and a value string. The value string replaces the value currently associated with that key in the DHT and the result is the old value string. This is also an asynchronous operation, so it returns a future of string, which will be ready to contain the old value resulting from the update. We've provided a helper function called localUpdate to assist in implementing the update function. This helper function accepts references to an unordered map and the key and value strings, performs the update locally on the map, and returns the old value result. So we'll break here to give you a few minutes to work this exercise, while we also have a live Q&A session with the presenters. For those who finish early, or who'd like to play around further with UPC++, I'll note the exercise directory also contains an exercise 4 that we won't be explicitly covering today. It demonstrates a slightly more sophisticated variant of the DHT, which uses RMA to transfer the values in order to achieve better bandwidth performance when the value strings are large. There's also a solutions directory with solutions to all of the exercises, and an examples directory that provides more fleshed out versions of all the codes that we've been discussing in this tutorial. So good luck with exercise 3, and we'll reconvene after a live Q&A to discuss the solution.